We have a habit in the AI industry of brute forcing our way to better performance. We build massive, monolithic systems known as dense models, operating under a simple assumption: scale up the compute, scale up the data, and the model gets smarter. The problem with a dense model is that it lacks precision. Imagine someone asks you what 2 plus 2 is, and to answer, you have to actively recall every single book you've ever read, your entire childhood, and the capital of Peru. You just need the math part of your brain, but the entire system activates. That is how a trillion-parameter dense model operates. Every single neuron, every parameter, must fire for every single word the model generates. 100% of the network is active, 100% of the time. Throwing millions of dollars of electricity and hardware at a prompt works if you only need a recipe for cookies, but it creates an unsustainable ceiling for latency and speed when you actually want an AI to do complex, multi-step work. In the industry, we call this the latency penalty of reasoning. If you want a model to act as a true autonomous agent, to browse the web, write code, test it, and debug it, it has to generate an internal monologue. It has to think out loud. To process that monologue, we use distributed computing. We link thousands of GPUs together. But for most operations to advance, all those GPUs have to finish their specific piece of the math before the entire system can synchronize and take the next step. This creates what engineers call the straggler problem. Imagine a group of 4,000 hikers navigating a trail. If just one person stops to tie their shoe or randomly gets a harder piece of terrain, the entire group of 4,000 people has to stop and wait. Dense models practically guarantee the straggler effect. Because every parameter is active, the workload is massive, and tiny random delays on a single GPU will stall a multi-million-dollar computing cluster over and over again. You cannot build a fluid, fast-acting agent on a stuttering engine. The architecture itself prevents the model from acting quickly enough to be genuinely useful. To solve the wall clock bottleneck, engineers are shifting towards sparse architectures. A recent model called Step 3.5 Flash approaches this by separating its 196 billion parameters into isolated pockets of knowledge. When it generates a token, it only uses 11 billion of those parameters. It uses a mixture-of-experts architecture, like a massive corporation with 288 specialized departments. When a word comes in, a central router evaluates it and instantly sends that task to only the top 8 most relevant departments. The rest stay asleep, consuming zero compute. But training a system to delegate this perfectly introduces a massive risk. During the training of Step 3.5 Flash, the engineers encountered a rogue expert. One specific node found a lazy shortcut in the data, realizing that the word numchi almost always follows the word import, and began screaming its answer, mathematically drowning out the other 287 experts. Trying to shrink the expert's neural weights didn't work. It just learned to scream louder with a smaller voice. So the team implemented activation clipping. They put a hard mathematical ceiling on the actual volume of the output signal. The expert could think whatever it wanted, but the router would only let it speak at a maximum volume of 10. Building an efficient, sparse AI requires intense micromanagement. You must restrict internal signals to prevent the model from gaming its own architecture. The active parameter count is only half the battle. The second major speed bump is attention, the mechanism a model uses to understand context. In a standard setup, every new word generated must mathematically cross-reference itself with every single word that came before it. If you double the length of a document, the compute requires quadruples. To cut that cost, Step 3.5 Flash uses sliding window attention. It reads like a flashlight in a dark room, illuminating a small circle of the past 500 words, completely ignoring the rest. This is incredibly fast, but it creates a glaring memory problem. If you introduce a character in Chapter 1 and your flashlight is currently scanning Chapter 10, the model mathematically cannot remember who that character is. The fix is a hybrid layout called S3F1. For 3 layers, the model uses the cheap flashlight view. Then, on the 4th layer, it triggers a floodlight. It uses full attention to look at the entire document, re-anchoring its global memory before dropping back. By narrowing the model's view 75% of the time, they saved enough memory to pack 50% more processing heads directly into the flashlight beam. The model runs with an incredibly detailed short-term focus, perfectly balanced against a broad long-term memory, without the latency penalty of full attention. This chart compares Step 3.5 Flash against major models. The blue striped bars represent Step 3.5 Flash, pulling even with massive models like Gemini 3.0 Pro. On rigorous tests like IMO Answer Bench and Live Code Bench, this sparse model secures frontier-level dominance on complex reasoning. That high score is a direct result of its cheap compute cost. Because it operates so efficiently, engineers utilize a technique called parallel coordinated reasoning. Instead of asking one slow, dense model to solve a problem once, they ask 8 identical clones to solve it simultaneously. They run parallel streams, taking slightly different logical paths, then coordinate to vote on the best possible answer. The efficiency of the architecture pays for the parallel processing. Speed doesn't force a trade-off with intelligence here. Speed provides the raw volume needed to extract the correct answer. This approach redefines what makes an AI system viable for real-world application. A model's total parameter count tells us how much knowledge a system holds in storage, but the active parameter count determines how fast it can actually deploy that knowledge. If an AI assistant takes 20 seconds to process a single command, you will inevitably stop using it. An autonomous agent repairing messy code or managing complex web tasks needs the agility to run thousands of internal steps, hit errors, and pivot immediately without bottlenecking a server rack. We are leaving the era where scaling intelligence required a massive energy footprint. We no longer need every neuron to fire for every keystroke. Efficiency is the new metric for intelligence. By moving from brute force scale to surgical precision, we finally have the architecture required to make autonomous agents genuinely useful.